Hello, fellow roboticist. This is Paolo. I'm your favorite robotic scientist, and it's an incredible year for us because I feel like there is an explosion of uh, robotic innovation, not just on the hardware side, but also on the software side, especially with what we call AI, reinforcement learning, and deep neural networks. There was a post that you can see on the top left from Jim Fan on the 24th of February. I'm recording this on the next day because I had some time to digest that. And it looks amazing, right? I mean, there is Sonic. I don't know what Sonic has to do with this. But it's just the acronym from this project. And yeah, let me zoom in on this tweet post or X post from Jim Fan. Well, it's talking about, if you take a GPT-1, so half of that, it's 42 million parameters. So we train this transformer called Sonic to control the body of a humanoid robot. It takes a remarkable amount of subconscious processing for humans to squat, turn, crawl, and sprint, which is true. We'll get into that in another tutorial. Sony captures the System 1, the fast reactive whole body intelligence, in a single model that translates any motion command into stable, natural motor signals. And it's all open source. So this is great. System 1, what does it refer by System 1? This is a famous book. If you just Google System 1 versus System 2, thinking. And yeah, you can, I mean, there's the original book. Let me see. Book, just look for that. Yeah, so Thinking Fast and Slow from Daniel Kahneman. Yeah. It's not really related to motion, to be honest. I think now people are kind of abusing that term. I wouldn't call this a system one thinking because biologically there are actually different mechanisms, but I mean, intuitively, it kind of makes sense call it a system one because it's kind of subconscious. Um, Although when you're a child, you have to learn that it is not that intuitive. So anyway, let's not kind of focus on this too much. It's all open source. Key insight, motion tracking is the one true scalable task for whole body control. Instead of hand engineering words for every new skill, we use dense frame-by-frame supervision from human mockup data. So what does that mean? Is they actually train this model from videos, well, or data from real humans performing tasks. So motion capture, well, it's kind of a generic term. We'll have to see in the paper. It can be body tracking. So I worked that in the past when I was doing my university course, where you wear mock-up. It's usually made for video games. So you wear a motion capture suit that looks like this. Let's see if we can find something online. Yeah, this kind of stuff. You probably have seen it in for movie making and all sorts of things. But yeah, you can essentially do it with the optical tracker, where you have lots of cameras tracking these little dots you can see there, or you can do it with the inertial sensor. So if you have a mock-up inertial sensors with I don't know if we have any videos. Yeah, this kind of, there are companies that do this, but essentially you attach to your body this inertial sensor unit, which is usually an accelerometer, a gyroscope, and magnetometer to track the orientation of your limbs. But it can also be video, so you can do like mock-up from video, and there's lots of models nowadays that can do that, right? So you don't have to wear anything special. You can you can essentially kind of from a camera track your body and replicate that in 3D. So I'm not sure what they, like we'll have to dig into this. And then the other important point is the data itself encodes the reward function. So configure your limbs in any human-like position while maintaining balance. So this is kind of important because in, let's say, reinforcement learning, you do need the reward function. And so it's on one side, yes, you want to copy the motion, but on the other side, like you don't want the robot to fall down, right? And so, yeah, we'll have to see what they mean exactly, but we scale humanoid motion reinforcement learning to an unprecedented scale. So what they did was to take 100 million plus mock-up frames and 500,000 parallel robots across 128 GPUs. Okay, NVIDIA Isaac Labs allow us to accelerate physics at 10,000 faster tick, giving robots many years of virtual experience in only hours of work clock time. So what does that mean? They took Isolab, which there will be also another tutorial about that one, but essentially it's a simulator where you can put a robot or any mechanical system and you can replicate an environment and you can essentially do that at scale. So you can clone, like you can do copies of robots in different environments, and you can run that in parallel for doing RL feedback or running an RL algorithm, right? And so apparently it took them 3 days of training, which is quite fast, but I mean, they did have used 128 GPUs. And well, the neural net transferred zero shot to the real G1 robot with no fine tuning. So that means like the output of 3 days of training was immediately transferred on a real. So they did sim to real, simulation to real. And the robot was able to sort of replicate immediately without any failures, which is impressive, I have to say. So then it says 100% success rate across 50 different real world motion sequences. So I guess these are 50 different type of scenarios. Okay, so since this is a policy, so it's a policy, it's like an algorithm that controls the motion. You need to have some sort of input. So what they say is they have a virtual reality whole body teleoperation. We have to see what that means. Human video. So just point a webcam to live stream motion. So that means, as I mentioned before, it's kind of mock-up, but simply from video. Text prompts. Wow, that's incredible. So you can just say, hey, walk sideways, dance like a monkey, kick your left foot, etc. Music audio, the robot dance to the beat, adapting to tempo and rhythm. Like, oh, that's interesting. And VLA foundation model. So we plugged in Groot and 1.5 and achieved 95% success on mobile tasks. So I believe what they mention here is that you have a very large action model, or I'm not sure. And this is a previous release from NVIDIA, which we can check later. And there are some videos here. It's all open source. And okay, let me see this video. I'm going to put the sound. Where is it? Yeah. Is there any sound here? Oh, I can't hear anything. I guess it's just a video. Whole body teleoperation. Okay, it's walking. So I'm assuming in this case is teleoperated. So there is a man somewhere doing this motion. Oh, you can see him here. You can see the hand here, right? He's teleoperating the hand. Okay, I'm assuming he's walking now. He's opening a fridge. You can see there are some sensors there. Huh. Wow. Okay, some peanut butter. Wow. I don't like peanut butter. Well, I guess they I think there's also some kimchi there. I'm not sure if it's butter or anything. And he's dropping it. Wow. You can see his hand on the left side. So this is definitely teleoperated, and it's probably... I'm not sure if there's any feedback from the hand. So it's probably has some tactile, and it knows when to stop. Oh, here we go. Here's the chap. He has a tattoo on the right leg. Imagine how odd that feels, because if you don't have any force feedback doing those motions, you have to sort of look at the actual robot to kind of see what's going on. So I would call these open loop feedback, as you, yeah. So you are the puppet master, and you have to see, to be very careful and make sure like your position match what's happening in reality. But still impressive. Oh, almost fell down there. Yeah. So this is cool. This is teleoperation mode. Okay, it's doing things. Okay, it's trying to take that dish. Okay, so one important thing here is that this is not autonomous navigation, right? So it's not SLAM, and it's not following. So there is a control, like the controller is the person. So there is no visual feedback, or I believe any tactile feedback. So it's just copying what a person is doing, which is still very impressive. But I think, yeah, 42 million transformer, but there is no feedback from the environment, right? So it's open loop control is essentially replicating motion, which is still impressive, but not, I would say, the way it was described, or it seems a little bit more. But yeah, so let's go and take a look at the paper. So I already opened some of the web pages. Let me close my page. This is the main page, which is beautiful. There's the paper, arxiv, docs and code. Yeah, so Sonic, what does that mean? It's supersizing motion tracking for natural humanoid whole body control. That's what it means. So there's no hedgehogs. There's this dude here doing something. It's kind of like running. Okay, these are all the autos made by NVIDIA. And well, let's see this one. What is this video about? One day at NVIDIA. Okay, it's coming up. Well, he's getting his badge. Teleoperated in real time. Okay, so there's still dudes. I can't see who is controlling him. Sorry. I guess the person is somewhere behind. Okay, he's grabbing his bottle. Wow, he's running at 1 p.m. It's running out. He's mowing the grass. Ha! That's well, in England we'll need that. What happened to this guy here? He's trying to sweep some leaves. All right, it's kind of running there. Oh, 4 p.m. What? I'm not sure what's happening there. 6 p.m. Okay, some dance moves. Well, I can tell you one thing: he's dancing better than me. All right, it's walking again. Yeah, so this is impressive. All results are generated using a single unified control policy. Really good. Okay. Skill montage. Let's look at this. Okay. Music is great. We've seen this before. Okay, it's boxing. It's kind of running there. Oh, this is interesting. You can clearly see some lag between the actual motion and what is replicating. Interesting. It's trying to get an apple here. Okay, it's pretty cool. I mean, yeah, it looks impressive. So probably these are the... Oh, here we go. Autonomous via VLA. Okay. So there is, yeah, we'll see into that. All right, so the abstract is here. Let's read into this. Okay, they're saying, yeah, we have, we can build billion parameter foundation models, but scaling gains are not being shown for humanoid control. Can humanoid remain modest in size? Target a limited behavior set and are trained on a handful of GPUs over several days. We show that scaling up model capacity, data, and compute yields a generalist humanoid controller capable of creating natural robust full body movements. Okay, so I think what they're getting at here is the equivalent of the chinchilla scaling laws for LLMs, because they talk about this three-dimension, the model capacity, the compute budget, or the GPU budget in this case, and essentially the parameters, right? Yeah, so okay, it's a natural scalable task for humanoid control, leveraging dense supervision from diverse motion capture. So once again, it's coming from motion capture data to acquire priors without manual reward engineering. So yeah, there is no reward signal. Like they didn't do any reward feature engineering. So we have a foundation model for motion tracking by scaling log3 axis. So the network size. Okay, so they tried anything from 1.2 million to 42 million parameters. Yeah, so the second one is the data set. So 100 million frames, which equivalent to 700 hours of high quality motion data. And compute, which is 9,000 GPU hours, which is the compute budget. Okay, so, besides the benefit of scale, we show that practical utility of our model through two mechanisms. Real-time universal kinematic planner that bridges motion tracking to downstream task execution, enabling natural and interactive control. Number two, unified token space. This is interesting. So you can control it with three different models. So yeah, the teleoperation, human videos, and VLAs. Oh, so what that means is vision language action models. Okay, so I got it right. But using the same policy, yeah, that's impressive. Okay, favorable properties, performance improves steadily with increased compute and data diversity and learned representation generalized to unseen motions. That's also very important. So yeah, so what they're saying is if I do, once I've trained this policy and I do something different, like, I don't know, instead of a monkey dance, I do a cat dance or something, it should be able to replicate those motions. Motion tracking and scale, so yeah, so this is imitation learning, what we call in RL imitation learning. So there is no, so when they were training this in the Isaac simulator, the error function, which we can see now, it's purely how well the robot imitates these mockup videos. Okay, so you have teleoperation. Okay, Kung Fu. That's not Kung Fu. I've done Kung Fu for many years. I'm not sure on the left side. That's not. I'm not sure what's this. Oh, he's doing something. Well, let me tell you one thing. But anyway, so there's video teleoperation. So as you can see, there's a camera and it's replicating those movements. There's VR teleoperation with key points. So they don't, yeah, okay. So it's a hybrid control using free VR tracking points. So you have the head and hands, okay, as the upper body, and a kinematic planner to generate lower body. So this is interesting. So they separate the upper body with these VR tracking points, and the lower bodies follows a kinematic planner. So I'm guessing the planner says go forward, 10, I don't know, 10 steps, and the policies take that, but also is following the person doing the head and hands movement, which is interesting. Um, I don't see the person doing that. Yeah, but there must be a person behind, so that's a bit confusing. Maybe there will be some other videos. And then there is VR teleoperation with whole body. So, okay, you can see the man here. Oh, I see. So he has the headset, two joysticks for the hands, and you can see on the ankles there are also two additional sensors, which I guess they are inertial and probably tells like the instead of the kinematic planner is essentially telling you where to go. Um, yeah, complete whole body motion have been precise. Okay. There we go. The dude is doing the same motion. He's trying to pick up a bag. Uh, okay, so and he's kind of following him. Oh, and then there's multimodal control. Okay, can perform expressing like dance motion synchronized to music. All right, so the choreography is generated by GEM. That's another model from NVIDIA. We'll probably do it in, I'm not putting any audio, but okay. So the motions are generated in this case by another model. Okay, okay, that makes sense. What else? Text control. So, okay, so they're saying, hey, backward walking, and it's doing that, or monkey movement. So you have natural language commands, but okay, they're still using this GEM model. Okay, it's kind of like cheating. And then you have the interactive kinematic planner. So our real-time kinematic planner enables interactive gamepad control. Okay, so somebody has a gamepad and is essentially going left, right, and you can style the actual walk with, happily running, stealth, and thing. Wow, that's pretty cool. So you have a gamepad. Okay, so I guess there is someone. I can't see the person operating, but I guess there's a joystick somewhere. Um, oh yeah, so you can do squatting, kneeling, and crawling. Okay, so you can decide where you want to go, but then you can have different modalities. Wow, that's impressive. Yeah, boxing. Okay, I don't know why boxing is a separate category. Policy's ability to track and execute dynamic, coordinated movement that require precise timing and balance. All right, so it's kind of more challenging. Well, let's look at this boxing thing. There's no audio here. Hey, oh, wow, almost fell down there. Well, as a boxer, well, I was an amateur boxer. This is, well, not impressive, I would say. I guess the problem with this robot is that if you look at this sequence of motion, there's no head control, so you'll have to chin down and you always have to protect yourself, right? I don't see that. So maybe the person that did the motion wasn't an expert boxer, but yeah, doesn't look good to be honest. uh, Also, the hip movement is wrong. Like there is no torsion of from all those punches. You start from the leg, going up and rotate the torso, but I don't see that. Um, but I think there is a limit. One of the other problems with this G1 robot is the degree of freedom. So they don't have a foot hinge, right? So to be honest, it would also be difficult from a robot to replicate the same movement. So we have, these robots have less degree of freedom. And so we do have VLA foundation model available, which it was mentioned actually, yes, in this tweet. So it's Groot and 1.5. They like this Marvel franchises or cartoons. But yeah, so they do. So yeah, there's a connection with this foundation model, which is Groot and 1.5, which works like this. Is also open foundation model. And essentially what you do here, you can say, pick up the apple and place it into the bottom shelf. You have vision encoder, text tokenizer. These are pre-trained. And then you have your robot state, Qt, which depends on the robot architecture. And well, you have feedback, yeah. So you have the feed forward, you have the encoder and decoder, you have the actual actions, the time t plus 1 plus the horizon, but then you take them back so that you can have this kind of feedback loop, right? But yeah, let's not get into this. I think this can be another tutorial. So anyway, so they say that we connect through the same universal control interface. Okay. And they have 95% success rate on a mobile manipulation task. So mobile means, yeah, it's sort of moving, and what is moving this apple, I think, what is grasping an apple. I'm not sure what's happening here. Okay, okay, it's taking an apple and putting it on a plate. So I was wrong. So there is, with this VLA model, you can actually have autonomous operation, right? So there is no person in this case. There is a command in text. I guess it was something like grab the apple and put it on a plate. And this was without any person, right? There was no teleoperation in this case. So apologies for that, but yeah, there is autonomous operation. Really cool. Okay, so finally we get this diagram. We have a diagram finally. Okay, so here's Sonic, universal control policy that seamlessly handles robot motion, blah, blah, blah. Okay, yeah, so this is the policy then. You have an encoder, quantizer, this beautiful universal token, and two decoders. Let me get into that. And so you have on the left side, you have these tasks. So you have the gamepad, as I mentioned before. So this to give you the direction only. Then you have this virtual reality or teleoperation. So you can either do it with a headset and the joysticks, or headset joysticks. And yeah, I was right. So you have this kind of leg sensors or ankle sensors, like a prisoner. Or you can have the gen mode. So the gen mode is you provide text or music, is going to generate some human motion, and is going to go on the human encoder. So I think this diagram means you can do gamepad control is going to go to this kinematic planner, and you have the robot motion that goes into the robot encoder, quantize, token, and the decoder. Or you can have, I'm assuming these colors means direction, right? So the blue one goes here. So these ones are not used. Or you can do, I guess, VR. So the VR point teleoperation will use the kinematic planner and the PicoVR toolkit. So the orange things, which will not use the robot motion maybe. So it's going to go here. It's going to go here. The VR key point and robot-like motion is going to activate the hybrid encoder. I'm not sure if it's going to go on the blue line because we didn't use this. So I'm assuming when you do this, it's going to use the kinematic planner, but it's going to feed here. So that's my assumption. Or what's happening here, if you use the whole body, which is the purple line, is going to go here and is going to go here. for human motion, and you have the human encoder. Okay, and the green line, I'm assuming, will just do that, right? So video genmo is going to get human motion, and it's going to be there. So yeah, we're going to sort of clarify this because I'm assuming is left to right blue line. So you will just use one encoder for this. When you use this, you're going to use the hybrid encoder, or you're going to use that. So I'm not sure if you're allowed, if it kind of works with all encoders. I'm assuming so, but from this diagram, it seems like it will use one at a time. But yeah, we'll have to check the paper. This is also a little bit confusing. There are two decoders here. So what's going on, right? I mean, you can't have parallel commands. And I think, judging from the pictures, what's happening here is that at the inference time, you will use this robot control decoder, right? But during training time, you might have both. And this can be used as a form of retargeting feedback, right? Because what you can do is, since the Uni3 robot is not similar, it doesn't replicate a real human body, it needs to adjust, right? And so it needs to kind of keep its latent representation consistent, but also it can't replicate exactly the same motion of a human. So I think there will be some sort of cross loss function here, but only during training time, and at the inference time when the actual robot is operating, is going to use these. And in fact, I mean, I think if you go back to these videos, I was talking about the boxing one. I mean, kneeling is probably, yeah, so injured walking. Yeah, as I mentioned before, this thing has less degree of freedom, right? And especially on the foot. So injured walking can't be 100%, right? Because maybe your foot needs to do something different, or stealth walking. But I think, yeah, I guess, let's see if there was something where I noticed there was a bit of a discrepancy. Yeah, I think you can see here something. Yeah, so you can see, the shoulder movements, obviously, it's probably all right, but the hips movement, it could be different. I think an interesting thing would be to go in the documentation of the G1, right? Because oh, it's in Chinese. Can't read Chinese. Oh, let's see if there is anything. These are all the joints. There should be like an overall. That's the hand. Remote control. I just want to find. There we go. That's the overall schema. So the G1 they're using is this one, I believe. So you have 23 degrees of freedom, 6 on the leg, 1 on the waist, right? Which means essentially, there we go. Yeah, this is obviously different from a human, so you have no spinal cord, but you can rotate, right? So you can rotate the entire torso, but obviously you can flex your body like that way, right? There's no spine, so when the robot have to copy that, it doesn't have a joint here, right? That can sort of tilt the upper body, if you know what I mean. There's no 2 degrees of freedom here. So it can't really replicate that, right? So it needs to rely on this representation to kind of say, hey, I'm doing my best, this is the best I can do with this degree of freedom, with this my body. That's the best I can do to follow these instructions, right? And so the same thing is, let me see, we have connecting rod rotation. So I think this allows the foot to roll left and right, and the calf to sort of pitch, right? So you have roll and pitch, but as you can see, the foot is one piece, right? There's no front foot. There's no flexing there, which makes it really hard to do boxing, right? As I mentioned before, when you do boxing, you have to flex your foot to generate enough power. So yeah, and also, as you can see, there is shoulder, elbow. There is no head joints, right? There's no joints on the head, which means he can't really bob his head to do or chin up and down, as it was mentioned before. So can't replicate that, right? That's why you need this feedback to make sure that it's there's a loss function that say, hey, that's the reality. No, it's the full body, but I have less, so I need to kind of minimize that error to do something meaningful, but also to constrain myself. So yeah, this is interesting. So that's what they're using. I think the hand, they don't have the full hand because it's like a claw. And I think there's a problem with this. The hand shouldn't look like that, so I don't know. Yeah, that's the hand they have, right? They show more fingers here for some reason. But that's definitely what they have in the video. You have 3 fingers, right? Like in Futurama, or what was the other cartoon? Okay, well, we'll do this in another video. As you can see, they have a radar and a camera, which I believe will be used when they use the VLA model, but in all the other modalities, it's like blind, right? It doesn't need vision, it's just copying the movement. So I think this module happens when they run the VLA model in parallel. And okay, you can see the difference. So yeah, 23 degree of freedom, 29. These are the default axes for the 0 point. Okay, we don't really have to care about that, maybe later in the discussion. And also interestingly, let's see, it has a 2 hours battery life. So this thing can only run for 2 hours. So yeah, so I think this Groot N1.5 will be plugged into the Vision. And we have this, this cross loss function, I guess, during training. We'll see later. And I'm not sure, it doesn't show the diagram for the VLA here, because like either you plug it on the QT, on the robot state, but then you get you get the actions already. So I'm not sure how the diagram doesn't explain that. I don't see how the VLA play a role in here. So we'll have to dig into that. Okay, so this was the page here. I got the paper here. So yeah, so you can, the cool thing about this that makes me really excited is that you can, I mean, this robot costs like $20,000, right? I don't have that money. I mean, $20,000, I think the Unitree G1 cost. Oh, it's cheap. Well, starting at 13,000, well, it's like in pound. Yeah. So it is expensive, right? Like $13,000 if you want to get that. I don't have that kind of money. And yeah, you probably want to run that on a simulator, so which they seem to have done. So you can do a sim to sim. Wow, in Mujoko. Okay, yeah, that will work. We can try to deploy this on a Mujoko. Okay, there's a quick start. Let me see. Okay, seems very well documented, so you can do a sim to sim loop. Oh wow, deploying a real robot. I wish you could do that. I can't. Okay. And oh, model checkpoints. Yeah, let's just do a quick check about these model checkpoints. So I opened up my Colab, which was disconnected. So let's see if I can do it. And okay, so what they have here, they have um, they have the source code which you can download, and it's here. Yeah, sorry, should have gone up. Yeah. No, I don't want to. I don't want to upload that. Yeah, I'll go up again. I don't want to go. I just want to go up one folder. Come on. Come on, Google. Mount Drive, refresh. I just want to go up one folder. Who is so stupid to have done this? Ah, home. All right. Cargo. Yeah. Mount. Let's keep these for a second. All right. I forgot to download this. Let's re-download this. Already exists. Well, let's restart session and run. Oh. Yeah, so they have the full repository here. Okay, with all the instructions. They've released an arcing face, I guess all the models, you can see them here. Okay, let's see what they have. Beautiful pictures and everything. Yeah, so it's true, they, interesting. So they have released the decoder and the encoder as ONNX format. Observation config, I don't know what's that. And the actual planner, which is suspicious. I don't know. I don't know what's suspicious. There's some sort of probably detection up in there. Okay. And okay, so you can download them, it's true. Yeah, it's only 66 megs. What is that? Come on. All right, this contains, yeah, exactly the Hugging Face space as it is. Or, well, let's see if you can download them individually, which I did already. I'm going to store Onyx so I can, I can do this. Inspect them and goddamn Gemini, what are you doing? Okay, so it's true, yeah. So the model parameter it released is for the encoder is 12 millions, for the decoder 10 millions, the planner is 185 millions. And so how much do we have? It's 207 millions across all parameters. So, well, let's go back to. So this is 42 millions, but we have 207 millions in total. So I'm not sure what Jim Fang was referring to. So, or maybe they released the biggest version. Yeah, this is a bit of a I don't know what happened here. So it's 42 millions, but I count more than that. So, not sure. Let's go quickly on the paper. Drama. Where is the paper here? Okay. I'll promise I will go through this. Yeah, blah. How many times they train that? Scaling up motion tracking. Baselines. So it looks good. Yeah, they should have explained that. Interesting. Yeah, I mean, they mentioned the GPU hours, model size. There we go, model size. So they have, I think they've done, yeah, three models, like sort of small, medium, big. So, oh, wait. They do have, no, this is the data side. So it's definitely 1.2, 16 million, and 42 millions. So that's mentioned here. But I can't much more. So I don't know what they mean exactly. Yeah, so they went from 1.2 millions to 42 millions. Um, mentioned that. And yeah, well, not good to say they have cheated, but these ones, oh, maybe they mean that the policy only, but that doesn't match. So yeah, I guess if you do the, oh, maybe what they mention is the policy. Yeah, that's weird. Maybe the planner. I mean, this is 22 millions if you just count that. So I'm not sure what's going on here. It's not 42 millions. Jim Fan, you cheated me. Ah, so we'll have to dig into this. It here is not mentioned. Yeah, what do they say? Well, we're not interested in the VLA for now. So yeah, if anyone knows why there is this difference, because I count, well, that's more than 42 millions. So, okay, well, that's something we can do later. So always check those papers. Okay, let's go back. So what they offer here? So they have, okay, so you have the all body control. Um, yeah, okay, we got that. So it's using CRUDs, and these are the VLAs. Uh, yeah, controllers. All right. We know we need some material for doing that. The C++ influence stack. That's good. Seem to seem. And you can install it. All right. TensorRT. We're probably going to do this in the second part because this is a lot of work. But yeah, okay, so you can download all the files. There's a quick start again to this. Well, I don't have a pick because I'm not sure how am I going to do this? Well, yeah, I need to fundraise some money. I'm not sure we'll be able to replicate that. Maybe there's a way to emulate it. Keyboard controls. Well, we should be able to do this, right? Because if I can just input the actual motion command to my keyboard. What's this guy doing here? All right, this is boring. Oh, okay. So you can use a keyboard. I guess we can use a keyboard. What was T? Don't press T. Well, imagine if there's a person here. I don't know. I guess it wasn't pre-recorded. Okay, interesting. But yeah, so it's Mujiko. Now, the interesting thing is they mentioned the Isaac Lab, but now it's Mujiko. I guess Mujiko is just for the playground, but Isaac Lab was used for the training part, which makes sense. Um, okay, so motion reference data. It's pretty cool. So we have everything. So I think this would be a very interesting tutorial. Um, let's go on the paper quickly before we go into part two. Okay, so this is pretty much the same thing as the tweet or X tweet. Okay, so this mentioned the network size from 1.2 millions to 42 million parameters, which I don't see. We have dataset volume, okay, and compute. Okay, and they mentioned these two benefits. Okay, so we connect motion tracking to downstream task execution, and we have a unified token space, yeah, that can support different input modalities. Okay, so the kinematic planner is also very important because, yeah, obviously you have to, you know, you have to move, so you have to. So kinematic in industrial robotics is direct and inverse kinematic. So direct kinematic is to say, I have to, I have to move forward. How do I do that? Um, so like I have so I give you an input and this needs to implement the kind of joint in joint space. You have to follow up the, like, if I rotate this arm like 90 degree, that's where it ends, right? So there is no inverse kinematic, so it's a sort of direct kinematic in this case. And then you have this kind of VLA hybrid modality. Okay, there's a lot of intro here. Yeah, we know this. Um, and yeah, so we are training data. Okay, so this is the most important part. Um, yeah, they're mostly limited to showing whole body motion tracking results on training data and not demonstrate many downstream tasks beyond motion tracking and navigation. Yeah, that's true, because these pyro studies, usually what you do is you just copy one motion, but you can't, like in the other example, like I want to move forward in different styles. It's just all these previous studies are copying thing. Um, yeah, so super size. So the S in Sonic, what does it mean? So that means they were able to basically take these 100 million frames at 50 frames per second. And okay, they did that on 128 GPUs budget. Yeah, with diverse human behaviors while maintaining real-time performance. Yeah, that's very important. So yeah, you don't want to have, um, you don't want to have behavior that is sort of lagging behind the actual person. Um, And then, yeah, if you have the motion tracker, so you can essentially apply that to downstream task. Okay, so what they've done is the universal kinematic motion generation systems for interactive control that enables goal-directed tasks such as interactive locomotion and game-like character control through kinematic planning in motion space. And second, we design universal token space that supports multimodal control, so you can do teleoperation, human videos, music, text. Oh wow, that's okay. And allows our motion tracker to directly interface with VLA. Yeah, I really want to see that they've done that, and diverse control modalities. So it's called Sonic because yes, it's supersizing motion tracking for nature human control. So nothing to do with Sonic. There's no hedgehogs. High precision teleoperation and interactive control, blah, blah, blah. Okay, so I think the first, okay, what do we do? Okay, still talking about these 100 million frames. Okay, they spend 9,000 GPU hours. Kinematic motion generation systems, so very important. That's probably what you're going to do then. And this universal token space. And evaluation, yeah, this is really important because then, this can work very well on simulation, but then like, yeah, what happens in reality where you have, like somebody doing something different, right? So they mentioned this robust sim to real deployment and successful integration with foundation model. So yeah, three main contributions. All make sense. They're using the Uni3 humanoid made in China with love from China, and we have seen that. Sonic ability for motion tracking. So yeah, motion tracking, teleoperation, and multimodal control. Interactive kinematic motion planning. Okay, so kinematic usually means, well, in the traditional sense, is direct motion, right? So you want to do something and you just translate that. But let's see data. Okay, once again, 100 million frames and exhibit remarkable generates of unseen motions. All right, and we have these metrics. Okay, so they have metrics, and yeah, the scaling up, comparison with baselines, and the real world evaluation, right? So this is where they put it on auto distribution. Okay, they have interactive motion control. Okay, video teleoperation. Yeah, let's go down. VR-based teleoperation, right? And final discussion. All right, materials and methods. Oh, this is good. This is juicy. This is what I'm interesting more. Same diagram as before. Oh, here we go. Motion tracking formulation. They're using PPO. Well, this is the most used RL method ever, right? So yeah, PPO for the win. Investor control policy. Ooh, that's interesting. 4 loss functions here. So yeah, we should look into that. So yeah, the loss function for the PPO, but all these three other ones. Yeah, we've seen that. And oh, the kinematic motion plan is 3.3 in this section. I'm just going to scroll really quickly because this is really cool. Multi-genmo, deployment. Now this is interesting as well because yeah, what's the control loop? So policy loop runs at 50 Hertz. That's impressive, quite fast. And the Unity-G platform using a built-in joint level PD controller. So I think, well, having done control systems, this is proportional derivative controller. And the learn policy outputs desired joint angles, which are passed directly to the PD interface. Yeah, so that's the forward kinematic in the traditional sense. You basically, and I've done a lot of work on this, but you essentially just say, hey, I want my angle here at 90 degree, and you give it to the PD interface, proportional derivative controller, which essentially calculate the input versus the output arrow and is able to hold that joint in that specific position or state. All components of the inference and management stack execute on board. Okay, so this is on board, yeah. Leveraging the on-device CPU GPU to minimize feedback latency and improve timing determinism. This is great. So this is actually real time. So it's 50 Hertz, so 50 times per second. And we assemble observation from the recent robot state, which I guess is the joint positions, and operator intent. So this is coming from the controller. So they evaluate the learn policies and synthesize, which means produce the joint space targets. Okay, so this happens at 50 Hertz. But then what they do is to ensure crisp, compliant actuation, these targets are streamed by a separate high rate process at 500 Hertz. So this is the, so it's like 10 times higher. Through the Unitree low-level API. I don't know what that is. We'll have to check that. Continuously publishing the latest user inputs, target motion command, without blocking the policy loop. Okay, so this runs at 10 times faster and it doesn't interfere with the policy loop. So yeah, interesting. So these targets. So I'm not sure if there's any interpolation here, because obviously it needs to fill these gaps. That will be interesting to see in the code. And ooh, yeah, let's see this. Yeah, this was my other question, like which encoder do I choose? And due to the decoder design, our system can seamlessly switch between different input interfaces. So yeah, the keyboard, gamepad, or network streams by changing the input encoder, enabling seamless transition between various tasks. So interactive gamepad control, teleoperation, whole body, video, and multi-load. So the user input is captured independently at 100 Hertz. Okay, so this is interesting. So the user input, so you see there are different schedulers here happening, which I will probably draw a diagram because there's no diagram here. Um, Oh, and look at this. The kinematic motion planner is employed at 10 Hertz, so 10 times a second, which proposes short horizon sequences based on the command from the input interface. Oh, here we go. This spans a temporal line with a 50 Hertz policy loop and smoothly blend it into control objectives, providing a motion interface without sacrificing responsiveness. Yeah. So you can see there is some sort of interpolation here. Each periodic process operates on consistent snapshots of the robot state. So I guess like they take the joint state as immutable. So I guess when they clock at 50 hertz or 100 hertz, they take that and they keep it, right? And we adopt the latest data wins convention to mitigate jitter, ensuring transit delays do not stall the system. Yeah, so well, this is quite common in real-time system. The easy way you can do it is you just say, hey, if I don't have time to process this, I'm just going to take the last, the last command or whatever, right? So you discard the other ones. But yeah, this is super important because you can see there are different loops at different frequencies to make sure that he has that kind of fluid movement, right? To avoid that kind of jitters. Both the interaction kinematic, motion planner, and the policy inference execute onboard the Jetson Orin GPU using TensorRT, which is the optimized version for real-time of TensorFlow, with CUDA graph acceleration. This configuration is reliable, low variance execution with, whoa, this is good, yeah. So you have 1-2 milliseconds for forward pass for policy, and 12 milliseconds for forward pass for motion generation. Okay, so the motion generation is around, well, it's 10 times slower than the policy generation, right? Resetting architecture emphasizes timing, robustness, and smoothness. It produces a stable motion while decoupled loops. Yeah, so they are decoupled loops. Isolate sensing and planning from control, stabilizing end-to-end latencies. Unless otherwise noted, all reported experiments use this onboard configuration. So it's 50, 10, 500, 100 Hz with timing logs enabled for diagnostics. So this is like a very important detail when you actually deploy this thing in real life. Because if you don't do this, you're going to have problems. So I feel like I will do a diagram later, contributions, and then okay, what do we have here? There's lots of people, man, lots of people here. Look at that. Okay, videos. All right. Okay, you've seen that. Oh, this could be what I was looking for. So there we go. So vector configuration, yeah, the quantizer, the encoder. Yeah, so you have all the three encoders, the two decoders, the IMLPs, multiple perceptrons, action dimensional, diagonal Gaussian. That's the critic. I guess that it's part of the PPO, and they have all the state dimensions and the motion command. You have 10 frames and the frame interval. Yeah, we'll have to figure this out. I guess that it's 2 milliseconds. No, that's lower than that. Yeah, I don't know what that means. I need to fusion frame. So they have R, H, and M. We'll have to figure out where these come from. Probably have to read that. Oh, the VLA predicts hand and wrist poses, base height, and navigation commands. Okay. Yeah, so Sonic is fast. System 1 whole body and System 2 for planner. Makes sense. Oh, reward functions. There we go. Training up the parameters. Yeah, this is all well documented. Tracking rewards. You have penalties. Oh, this is good. Yeah. This is where we have to go through that. One thing I'm noticing here. So domain randomization, what is this? When you're, putting this robot in the Isaac simulator, you have to provide some variance, right? And this all makes sense. So physical parameters, what does it mean? You have the floor where this robot operates, and so what they did and say, well, let's increase the static friction coefficient, so like the sort of roughness of the surface in US, and they did a uniform distribution between 0.3 and 1.6. Dynamic friction is, if you remember your course in robotics, is essentially velocity dependent. So if you're moving an object into a surface, the more you go faster, the worse the friction is. So they simulate that. Restitution coefficient, I believe, is the bounce energy. So if it's 0, it doesn't give any energy back. So it's like working on, I don't know, concrete. But if you're working on a judo mat with some sort of electricity, you get something back, right? Default joint positions, I believe this is where you start from the beginning. So we have seen the Unitary one start like sort of a upstanding position. So obviously you might want to change that when you start. You have different body positions. Base comb offset, I think he's the center of mass. I need to look into that because there are three variables. So maybe it's like when you're like, I would say the center of mass makes sense. You switch it when you have maybe wearing a backpack. I saw a video where the guy was wearing a backpack, right, or carrying something. Your center of mass will change. So I guess they're doing that. So this is for physical, and then root velocity perturbations. Oh yeah, this is the classical test when, like, I think you've seen this post, or maybe Unitary G1 kick. I don't know. When they kick those robots, right? Like this guy's kicking that, so essentially robot kung fu. But the idea is that somebody is pushing it, so they are going to kind of add some sort of external external interference. So like, yeah, I'm going to push you between 1 and 3 seconds, and I'm going to change your angular velocity. I think root means the reference of the robot. I don't know. I have to see this. So essentially, it's sort of going to give it a spin, and also like a push linearly, like I can either rotate you or push you into different angles. So yeah, this is, I guess it's just to make it sure that someone knows the robot is not going to fall down, or sort of move away from that position or from that sequence. And then target motion perturbation. So I would say this one is where you have mostly like electrical noise or sensor noise. So like, if if the state is, if I give you like a command and say like 5 degrees or 0.5 radians or something, uh, the hardware might not um, follow it exactly because this PD controls. So I think this is to essentially, you have a different robot. So the robot that you obviously the robot that is in the simulator, it's an approximation of the real robot, right? So you will, there will be some error, right? And I think they introduced this jitter to make sure that there is enough leeways between the simulation and the real robot, right? And so they all make sense, especially for sim to real and uniform distribution. What I don't see here, which is very interesting, the floor size is not randomized. So the floor is always flat. And if you look at these videos, as you can see, this is flat. I don't see anything with a slope except, well, could be a perspective, but I don't see anywhere in these videos where the robot is in on a slope. And I think that is because of that. So they haven't trained the robot for a different slope because it's not there. So yeah, I'm not sure. It will probably fall down. That's my guess. But yeah, all the other parameters are here. And I guess I will have to do some maths in the next tutorial to kind of figure out the mystery of 42 million parameters. It's probably the sum of these. I will have to count all of that because they have dimensions. But yeah, that's another thing I want to understand. The hardware is fine. So yeah, this paper is 26 pages, but it's very good, detailed. And the next tutorial, I think I will look into before looking into result, what I'm going to do is I will look at the training set. So training set, where is it? Training sets. Yeah, because training set Sonic is not trained on the AMAS dataset. Okay. I already used conditional for random subset of retargeted AMAS. Okay. In twist. Okay, so I really want to see where is this 100 million frames. I need to see that. So I just want to see where the existing dataset was and how was it validated on this other one. And then, okay, comparison to baselines, real world evaluation. And then I really want to dig into this, right? This is the most important part is the training setup, right? And how do they split these three encoders? And okay, yeah, so we look into that. It's very detailed. Well, at least we know it's PPO. So if you were curious about the RL, it's the nothing fancy is PPO, but with some twist, with different loss functions, multiple loss functions. And yeah, we'll have to look at the reward signals and the domain randomization. So yeah, I think I'm going to stop here because there's kind of a lot of material. And what I will do next is I will also start to prepare a little bit of code and like install the Mujako. I'll see if I can replicate that um, to see if we can run that. So yeah, um, I'm going to stop now, and hopefully I will see you in part number 2, where I'm going to look at some of the things that we found we had a bit of a uh, discrepancies with a billion parameters and randomization conditions. And yeah, the decoder, like how does the decoder works, and also how the VLA plugs into the main policy. So yeah, we're going to look into all of those, and well, see you in my next one. Bye.